Okay, for this video, I'll be going through pure physics magnetism tutorial. Okay, question 1, they want us to sketch the magnetic field pattern on each diagram. Okay, so part A, it is just a simple bar magnet, north and south. So just need to take note that the magnetic field lines comes out from the north, okay, and enters the south. Okay, so make sure that the field lines do not touch or cut each other, okay, so usually in exam 1 mark will be given for the correct pattern, okay, and the other mark will be for the direction. Okay, so just take note it comes out from north, okay, and enters the south. Okay, so part B, there are 2 bar magnets with the north facing each other. So because the field lines cannot cut or touch each other, that's why the field lines actually goes up without touching each other. Okay, so then over here there will be no magnetic effect, okay, because there's no magnetic field lines, okay, provided that both magnets are of the same strength. Okay, then part C is north and south facing each other. So the field lines will be coming up from north and then will be entering south. Okay, so take note there will also be this field lines that goes from the own magnet's north pole into its own south pole. Okay, part D, there actually is a soft iron here, and soft iron is actually a soft magnetic material. That means it is easy to magnetize and demagnetize. So the outside is air. So compared to air, soft iron is like a magnetic material. So the field lines will actually prefer to flow through the soft iron. Okay, and therefore the soft iron actually is able to concentrate the magnetic field strength. Okay. So we see this in the electromagnetism and electromagnetic induction. The soft iron is actually there to concentrate the magnetic field lines, right? Because the field lines actually prefer to flow through the soft magnetic material. Okay. So similarly for part E, we have a soft iron, right? So therefore, the field lines will be flowing through the soft iron. Okay, just take note that you do not draw until the field lines cut each other. Okay, now we have north and north facing both sides. So we also still have all these field lines going from north to south. Make sure they don't touch. And over here, again, make sure they don't touch. And just take note of the direction. Okay, G is actually a coil of wire. A coil of wire, we actually call it a solenoid that actually has current flowing through it. Okay, when we supply current, it will flow through the coil of wire, and usually it's made of copper. Okay, then we look at the key. See, the cross here means that the direction of the current is into the page, right? Remember, the dot and cross doesn't mean direction of current, doesn't mean direction of magnetic field. It just means direction. So this is into the page, this is out of page. Okay, coming towards us, coming towards the reader, which is us, and this is into the page, which is going away from the reader, going away. So in this context, they are using the cross to mean current, the direction of current, and they are using the dot to represent the direction of current that's coming out of the page. Okay, so because this is a current flowing in a solenoid, so whenever current flows, okay, very important, the link between current, between electricity and magnetism is when current flows, it produces a magnetic field. Okay, so now in this case we have current flowing in a coil. Okay, so we have to apply right hand grip rule for solenoid. Okay, so where your thumb represents the north pole, okay, the position of the north pole, and your fingers represent direction of current. Okay, so the current is coming out and entering. Current is coming out and entering. So you should be gripping using your right hand, and your right hand should look something like this. You can only see the knuckles, okay, and not the nails. Okay, you can only see the nail of your thumb, right? So you are gripping. So this represents the direction of current. The fingers represent the direction of current. Okay, so that's why north is over here, south is over here. So now that you know where's the north and the south, you know that the field lines come out from the north and enters the south. Okay, so some of you actually drew this correct. Okay, coming out from north and entering the south. But one thing that many students didn't do when I was marking is within this coil there is actually magnetic field lines. So some of you just drew from here to here, so leaving the inside empty, which is not correct. Okay, so the field lines is continuous. Okay, so it's as if I have a bar magnet, right? Remember we said that the bar magnet is having a lot of little atomic magnets, so they are all aligned this way. So if here is north, here is south, they are all aligned this way, and this is the direction of the magnetic field lines, right? That's why they come out from north, okay, and enters the south. So within the magnet, we also have the magnetic field lines going this way, okay? And since this is an electromagnet whereby the current flowing, it produces a magnetic field, there should also be magnetic field lines within the coil itself, okay? Okay, question 2. Two metal rods A and B are of the same size, are placed inside a solenoid as shown. It is connected to a battery through a switch S. So you see when current flows, it produces a magnetic field. Okay. Okay, let's read on. The two rods are made of iron. Take note that iron is a soft magnetic material. Okay, so it's easy to magnetize and demagnetize. Then they want us to explain the following observations that are made with this equipment. After switch S is closed, current flow, the metal rods roll away from each other. Why do they roll away? Okay, so the answer is when switch S is closed, a magnetic field is set up, right? Current flows, produces a magnetic field, okay, within the solenoid, and this induces, the keyword here, magnetism in rods A and B. Okay, since the adjacent ends of each rod are magnetized with the same polarity. So if, example, this side of rod A is North Pole, this side of rod B will also be North Pole. Then this is the important concept. Since like poles repel, they will repel each other and hence roll away from each other. Okay, when the two iron rods are replaced with steel, so steel is a hard magnetic material. What does hard magnetic material means? It means that it is difficult to magnetize and demagnetize. Okay, so when the switch S is closed, and after some time, then we open the switch. Why after some time then we open the switch? It's because the time is needed for the current to magnetize, or time is needed for the magnetic field produced by the current to induce magnetism in steel rod, because steel is difficult to magnetize and demagnetize. So after some time, they are finally induced with the similar poles. They will repel one another, and then when switch S is open, the two rods will remain apart, right, as they remain magnetized and continue to repel each other, because steel is demagnetized, cannot be demagnetized easily because it is a hard magnetic material. Okay, so when you read the question, you see iron and steel, straight away you must think of soft magnetic material for iron and hard magnetic material for steel, and that it is easy to magnetize and demagnetize for soft magnetic material, and for hard magnetic material, difficult to magnetize and demagnetize. Okay, question 3, we see iron armature. Okay, it shows a model circuit breaker, right? The current enters at X, passes along P, Q, R, S, and leaves at Y. Okay, So this is just a model. Now state the magnetic pole facing the iron armature. Okay, so the current is entering at X, okay, flows along P, Q, and then it will flow through the iron armature because iron is a conductor of electricity. And over here, the coil of wire is wound this way. So I will actually need you guys to draw this direction of the current flow, because then you can apply your right hand grip rule for solenoid. Right hand grip rule for solenoid. Okay, so the fingers will represent the direction of the current, okay, which is this way, right? Therefore, I need to grip with my right hand, and I can't see my fingers. Okay, I can only see that they are going to grip in this direction. Okay, and therefore this part will be the north. That means facing the iron armature, it will be north. Okay, so it is very important to draw all these little arrows and use your fingers to represent the direction of current. Okay, so describe how the circuit breaker works. When there's excessive current, right, that's what we learn in practical electricity. Due to an electrical fault, the large current or a current surge will cause the solenoid to become a stronger electromagnet. Okay, so do not miss out this word stronger, because when current is flowing, it will produce a magnetic field. But just that the normal working current, okay, it is not strong enough. The magnetic field produced by the normal current is not strong enough to cause the iron armature to be attracted to the iron core, right, to the electromagnet. But when there's an electrical fault, a surge in current will cause the solenoid to become a stronger electromagnet. So this is actually the key word here. You can't, some students will make the mistake, just say when there's an electrical fault, the large current will cause a solenoid to become a electromagnet. But it was already an electromagnet whenever current flows, right? So do not miss out the word stronger. And when it's stronger, it is strong enough to pull the iron armature towards it. So loses contact, creates an open circuit, and current stop flowing. By the way, circuit breaker should be connected to the live wire. Okay, just a kind of revision. Now state the effect on the operation of the circuit breaker after each of the following changes and give a reason. So you need to explain. Now what happens if we remove the iron core? So just now we have actually drew the magnetic field lines through the iron, which is a soft magnetic material. So the iron core basically will concentrate the magnetic field lines, okay, or magnetic field strength, right? So without the iron core, right, the magnetic field strength will not be as large, right? Therefore, we will need a larger current for the circuit breaker to switch off the electrical supply, because now the electromagnet is weaker without an iron core that concentrates the magnetic field lines, okay? Now, what happens if we increase the number of turns on the coil? Take note, it is not about increasing number of coils, okay? It's increasing the number of turns, okay? So, a smaller current is needed because now I have more turns, right? Because more turns will create a greater magnetic field strength, right? So, we only need a smaller current to exceed the working current for the circuit breaker to work. So in this way, you can sort of fine-tune what is the circuit breaker rating, okay? Now, what happens if we use AC instead of DC? Now, AC means the current changes direction. Current changes direction. Okay, for Singapore, the current is 50 hertz. Okay, that means the current changes direction 50 times a second. Okay, for DC, the current will remain flowing in one direction. So when we use AC instead of DC, there's no effect because it will continue to work. Because once the current exceeds the circuit breaker rating, the electromagnet will become strong enough, right? It will create a stronger electromagnet to create the open circuit by attracting the soft iron armature, right? So whether is it AC or DC, it will still work. By the way, in Singapore, current is or electricity is transmitted using alternating current, which is our AC. Okay, and this will be covered in electromagnetic induction. Okay.